Okay, I'm going to assume that you watched the video, but I'm still going to coach you is to try, as we do these problems, not just to do them to get an answer, but to do them to understand the concepts. And so I know watching the video the first time, probably a lot of it goes over your head, and after you do problems, then you might have a better idea. So it's probably a good idea to watch the video once in the beginning, and then maybe once or twice in the middle or toward the end of doing the assignment, where it all might come together and you would understand it. So here we have in number 2, I'm going to start with number 2, and you'll understand why in a minute. So you have a negative charge, and I'm not drawing all the field lines, but there's probably 20 or more field lines in that picture. And they're going in because field lines go toward a negative charge. They begin on positive and end on negative. And what we know is that there's an electric field. And remind yourself what an electric field is. If I pick a point, that the electric field there, since this is a point charge, the electric field at this point, whoops, my pen, is going to be E equals K times the charge there, divided by R squared, where you always want to remind yourself that R is the distance to the charge, from the point to the charge, or the charge to the point. So that's how we calculate the field. And if we drew a vector, it would be in this direction. The field lines are another way of representing it. But now we're doing energy. So this charge also has energy, right? This point has energy, because if we put a charge here, let's put a positive charge there, the charge is going to be attracted, so the force is that way, and it's going to go this way. If we release this charge, it'll move toward the positive charge and gain kinetic energy. So this point has a potential, which is the potential energy per unit charge that we put there. In other words, we want the energy per unit charge. That's joules per coulomb, and that's a volt. And so the way we calculate the potential at this point is the equation for the potential, and it looks almost like identical to the field. Two important differences. One, this is R and not R squared, and two, potential is a scalar, not a vector. So from this equation, you know that the way you would get the energy, if you put a charge there, the electric potential energy, would just multiply that second charge times the voltage. So the voltage here depends on 3 things. It depends on this charge. If we double it, the voltage will double. It depends on the distance, and that's it. So if we keep the charge constant and we keep the distance constant, the voltage will be constant. And a constant distance from the charge will be a circle. So the circles you see in the diagram are locations of equipotential. The potential is the same over all those circles. And so any circle you draw, now what would the potential here be? Well, you'd put in K, you'd put in Q, and you'd put in R, and you'd get a number. And supposing it were 20 volts, then everywhere on this line would be 20 volts. Actually, a negative 20 volts, since it's a negative charge. And if we go where R is half the distance, we would have a circle where everything was 40 volts. And if we went out twice the distance, we'd have a circle where everything was 10 volts. And so the diagram you're looking at shows black lines, which are field lines, and red lines. I should have used the red. And red lines, which are equipotential lines. And one of the things that will come up in this question is that since energy changes when you do work, that if we go along here, there's a force, right? If you have a charge here and there's a force in this direction, and you move with the force, you're going to get energy. You're going to get acceleration and kinetic energy. If you move away from it, you have to do work, and you increase the energy. But if you move in the circle, you're moving parallel to the force, so the work is zero. So the work it takes to move a charge around here is zero because the energy and the potential stay the same. Those are all the concepts that you're trying to learn this week. So let's go through the listings. The black lines are electric field lines. Correct. The black lines are electric field vectors. No, you should understand that the difference between a field line and a vector, that they're different. Okay, and you might have to go back and review that. But a field line is not a vector. A vector is an individual arrow at some point. A field line is a continuous line that in a way combines vectors. Now, what you're reading on your screen may be different from what I'm reading because these get jumbled, but I'm just going through these for you. So the red lines can be used to find the direction of the field. Yes. The field is always perpendicular to the red line for reasons I just mentioned. So if you have the red lines, you could generate the field lines. If you have the field lines, you could generate the equipotential lines. Why? Because they're all always perpendicular. That's explained in the video, so I'm not going to dwell on that. The red lines can be used to generate the black lines. Yes, red lines can be used to generate black lines because the red lines are equipotential surfaces and the black lines are perpendicular to them. Red lines contain information about the magnitude and the direction of the electric field. The answer is yes, because the field line direction is always perpendicular to the red lines. And the rate, this is sort of beyond what I expect you to know, but it is true that the rate at which the lines increase or decrease will give you information about the magnitude of the field. So if the field is strong, the potential is going to go up or down very quickly. And a tangent drawn to a red line is not the direction of the field. The direction of the field is perpendicular to the red line. Black lines indicate the direction of motion of the electric field at any point. That's a trick question. The electric field, it doesn't move, it's static. So the electric field, it's just the direction of the electric field. There's no motion to it. There is a single but different value associated with each black line. That's true of the red lines. It's not true of the black lines. A black line shows different field strengths as you move toward or away from the charge. Think about it. Red lines are representations of electric flux. They have nothing to do with electric flux. Electric flux is field lines passing through surfaces. And each red line can be represented by a single number. That is correct. Each line is a unique single potential. Black lines cannot be used to generate red lines. We already said that. That's wrong because it is true. Black lines are different quantities, that's true, that are entirely independent of each other. That is not true. They're always perpendicular to each other. And the red lines are equipotential lines, yes. Okay, now let's go to number 1. So in number 1, we're calculating the potential at this point, and we're comparing them for all the different ones. So this is B. I'm going to do B. And if you might just try doing it. Pause the video and see if you can do it. And if you can't, just hang on. So I'm going to pause, actually. So we should do one of these in full detail. Make sure you understand it. Once you've got it, you can do them pretty fast. So I'm doing B. I don't think these get shuffled, so should have the same B. And I drew the figure and labeled everything. So the way we're going to get the potential at this point is we're going to add V1, V2, and V3. Just like if we were getting the field at this point, we would add E1, E2, E3. So it's important to start with this statement. But what you want to realize is these are scalars. They don't have a direction. So don't make the problem harder by putting in vectors. We're not doing field, we're doing potential. And the potential is calculated for point charges. These are point charges KQ over, so K, Q1 over R1 will give us V1. So V1 is K, Q1 is positive Q, and the distance is 2D. The second one is K, a negative Q, over a distance of D. And the third one is K, positive Q, over D. Now notice the K, Q, and the D are common to all of them. So it's just a distraction, really. So we pull the K, Q, D out. And what's left here is 1/2. What's left here is a -1. And what's left here is a +1, and when you add all those together, you get 1/2. In other words, potentials can be positive and negative. These two cancel each other out, and the total potential is just the potential of this one. So you should be able to go through the rest of them, and I hope you can just drop the KQ over D. Just think of this as a distance of 1, this is a distance of 2, and if you have one where the point is over here, then you might have a distance of 3. Okay, hopefully that will get you through that one. Okay, we'll skip number 3. Number 3 is similar to number 2, and I spent a lot of time on that. So let's go to number 4. You can read it. We have an equilateral triangle of charges of all the same sign and magnitude. And there's two parts. First part, we're going to find the electric field at the midpoint. The electric potential. So I write down the usual equation. The electric potential at this point will be the sum of 3 potentials due to each of the 3 charges at that point. And so V1 is going to be KQ1 over R1 and so on. So let's see if you can do this. And if you can't, wait and see what I do. Okay, so I did for V1, I did KQ. They're all going to be Q over the distance from the point. So that's S over 2, and it's not squared, right? And then this one is going to be the same thing. And then here we got to get the distance from the point to there. And since this is S over 2 and this is S, you have S squared minus S squared over 4 gives us 3/4 S squared. And when we take the square root, you should find this distance is the square root of 3 over 2S. Forget the S. Okay, as usual, mostly trig and algebra. So we said this is S over 2. This is the square root of 3 over 2. And the KQ over S factors out. And if you do without making a mistake, which I don't think I did, you get 2 plus 2 plus 2 over the square root of 3. If I add that together, it simplifies to this because we don't like leaving a square root in the denominator fraction. And if you calculate this, you get the 0.15. So that's 2 of the 4 answers. Now we want to get the point at the middle, right? So let's put a point at the middle and do it. Why don't you try doing that on your own? So this is fairly easy. The midpoint is equidistant from any of those. And so the potential is just going to be 3 numbers. Remember, it's a potential, not a field. That's going to mess you up, not vectors. So just adding 3 numbers, and they're all the same. Why? Because the Q's are the same, the K's are the same, the distance is the same. And so V1 plus V2 plus V3 is the same as 3 times V1, since they're all equal. And 3 times V1 is 3kq over the distance to the center from any charge. So now you got to figure that. So it's mostly a trig problem. Go ahead, see if you can get that. Okay, here's how to do the trig. Put the point there, draw this triangle. I'm sure there are other ways, but this is, I think, a pretty good way of doing it. And so this is the distance we want. Drop a perpendicular. By symmetry, that's going to pass through the side, so that this side is s over 2, and this side is 30. And this is the hypotenuse, so you trig to get that distance, and then finish the problem. Okay, since we know the adjacent side and we're looking for the hypotenuse of this triangle, I use cosine of 30, and the cosine of 30 is the square root of 3 over 2. You could do this by number, but you have to get it for the multiple choice thing. And so I have that the r to the center is this side divided by the cosine, or s over 2 divided by 3 over 2, so the 2's cancel, and you get s over 3. Now you got to take the s over 3 and substitute it in there, and guess what you get? You do get 3 times the square root of 3 kq over s, and now you're done with this one. Okay, I skipped 5 because I think 4 should cover that, and now 6 and 7 is the square. So I think what's the easiest one is going to be the point in the middle. And then there's the point here. And so for this one, you should be able to do this, right? Anyway, for this one, the distance, in every case, you write this equation down. So this is the beginning point. Well, actually, the beginning point is the diagram. Then we write that the total at either point is going to be the sum of 4. In this case, the 4 are all equal, right? Equal charges, and the distance is equal. I hope you know that if this is s by now, if this is s and this is s, this is the square root of 2 times s, and so this will be the square root of 2 over 2 times s, that distance, right? Simple trig. We've done this enough. And so in that case, you're just adding 4 times any one of those numbers because they're all positive. In the case of this point, 2 of the distances are s over 2, and the other distance is this. We've actually done this before. I think it's the square root of 5 over 2. I'll let you figure that out. And with that, it's just a matter of doing the algebra. So I'm going to leave that up to you, and if we change 2 of them to negative, then you just have to make the adjustments for positive and negative potentials. And once again, remember, these are potentials, they're not fields, they're not vectors, you don't need to be worrying about direction. Okay, problem 8 and problem 10 are on the hydrogen atom, and problem 9 on another important historical experiment, the Rutherford scattering experiment that tells us about the structure of the atom. So here, using the physics we're learning this week, plus some basic mechanics from last semester, we can understand the basic fundamental workings of the hydrogen atom, and we can use that to understand the Rutherford experiment, where Rutherford figured out a very important aspect of the structure of matter, such that the nucleus of the atom contains most of the mass, and most of the volume of the atom is just a cloud of electron energy, really, around the atom. So here's the simple model of any atom: a nucleus with positive charges and sometimes neutrons, and a negative charge, and the simplest atom is hydrogen, 1 proton, 1 electron. So a little bit of background information. The charge on the electron is the fundamental unit of charge. We studied this back in week 1. It's 1e. It's 1.6 times 10 to the minus 19 coulombs. And so in energy, if we take an electron, remember energy is Q times V. And so if we take an electron and use that instead of coulombs, and then we use the volt, so you take an electron and you let it go through, say, between 2 plates of 1 volt, or you let it go through an electric potential change of 1 volt, you will have 1 electron volt worth of energy. So the electron volt, just like E is a small unit of charge, the electron volt is a small unit of energy of the same proportion. So 1 electron volt, that's a unit of energy, is 1.6 times 10 to the minus 19 coulombs. Because if you put 1 times 1.6 times 10 to the minus 19 coulombs and multiply it by 1 volt, you will get that much energy. But instead of using the coulomb, we use E, the electron charge, we get this. So this is a way of talking about small energies, and we'll use it during this assignment and this lab, so it's important to know that. The other thing is that the charge on the proton is the same as the charge on the electron, and so it's 1e, and this is negative 1e. So when we calculate the force of the proton on the electron as it moves, this is like a moon moving around the Earth, that force, that electric force there, is going to be K Q1 Q2 over R12 squared. And so the K, of course, is K, Q1 is E, Q2 is E. We're just calculating the magnitude, so it's E squared. That's the product of the 2 charges of the same charge. And the distance is the radius of the atom that we're given, the radius of the hydrogen atom, squared. And from first semester, we know that when something moves in a circle, it's accelerating because it's changing direction. And so the force has to equal the mass times the acceleration. That's centripetal force. This goes back to first semester. But the acceleration, when it's moving in a circle at constant speed, is v squared over r. And so in order for this to be in a stable orbit, just think about it physically. If the electron is moving too slow, it's going to be pulled into the nucleus, and if it's moving too fast, it'll escape the nucleus. So there's, in order to have a stable orbit, like we learned last semester, it has to move at just the right speed. It can't move faster, it'll escape, or move slower, it'll collapse. And so that speed is found by matching this condition. But actually, since we're doing this problem to understand the energy, what we want to know is the kinetic energy. And so when you look at this equation, you'll see that mv squared is almost the energy. So let's find out what the kinetic energy is. And this is how we do it. This is the force. Right? This is the force, the Fe is the centripetal force, and so this force must be equal to the mass times the acceleration. So let those two things be equal and see if you can find the kinetic energy. Try it on your own. And if you don't think you can do it, don't be lazy. Watch me. So I'm going to do this. K E squared over R squared equals m v squared over r. That is the same r, by the way. That's the radius of the hydrogen atom, because that's what we're talking about. And so I multiply both sides by r. And I divide by a half. Why? Because I'm looking for the kinetic energy. Why did I do that? Because I can see mv squared is almost the kinetic energy. So I'm smart, you're smart. And so you left with that 1/2 mv squared equals 1/2 ke squared over r. Notice ke squared over r, that has the units of energy. That is like a electric potential energy. Anyway, what we found, don't get lost, what we found is we found the kinetic energy that the electron has to have if it's in a stable orbit, and this is the amount of energy it has to have. We can calculate it. Now, compare that to its potential energy. Well, the potential energy, we know how to do that. Don't forget, you know how. The potential energy is simply K, Q1, Q2, 2-point charges, right, over R. And so in this case, what is that? It's K E squared over R, the radius of the atom. And so what you can see here is, oh, and this is negative. That's important. That is important because one of the charges is negative. So the potential energy is negative, but the atom has a positive amount of kinetic energy. So this would be the energy if the electron was sitting here and the proton was sitting here and I were holding them apart. This would be the amount of energy that it would take for me to take the electron and move it away, right? Because it's being attracted. I have to push the electron away. But the electron isn't still. It has this amount of energy because it's moving. But this is only half of the potential energy that has to be overcome to remove the electron. And so when we subtract, or when we add the kinetic energy to the potential energy, what's left is the energy that we have to do work to remove the electron from the atom, and that's called the ionization energy. And so you can put the numbers in and calculate all that. Okay, hopefully what I showed you will get you through problem 8 and 10. If not, you'll have to ask me. And now number 9. And what's really, I hope you appreciate, very exciting about this semester is that we're using the basic physics we're learning to understand many, many amazing scientific discoveries that occurred in the late 1800s and the early 1900s, such as an understanding of the hydrogen atom. And now one of the most important experiments leading to a Nobel Prize, an understanding of the structure of matter. So if you think about, we're beginning to know about electrons, protons, and neutrons, and people naturally just assumed that atoms were sort of a smooth arrangement of matter. And so Rutherford came up with the idea of testing the structure of matter this way. So if you know about gold, you know that it can be pounded out into incredibly thin pieces of metal without falling apart. And so he thought, okay, we'll take a gold foil and hang it up, small piece, and then we'll also radioactivity had been discovered, and it knew that radium emitted these high energy particles called alpha particles. So we'll take a radium source and we'll put it in a lead box where we're protected from it, and a little hole in the box so that the alpha particle emissions can just come out the hole, and they will travel towards the foil. And from what was known at the time about the thickness of the gold foil relative to the energy of these particles, Rutherford was predicting that the particles would just go right through without any deflection. And so you need to detect the things, but these things are high energy, so when they hit certain materials, they cause a spot of light. So we surround this by a fluorescing screen so that when the particles hit, we'll see these little flashes of light. Anyway, so this is pretty much a simplification of it, but what happened was they did this, and sure enough, they weren't surprised. The particles seemed to go right through the gold foil without any deflection, only they noticed that occasionally, and quite rarely, a particle would appear far away from that path. And so they extended the detecting screen all the way around and found that on even rarer occasions a particle would bounce back, would strike the gold foil and bounce back. So 99.9% go through, some very small fraction deflect a little bit, or occasionally they come right back at the detector. And so if you think about this, how could that be? What would be going on? And the logical explanation is that the matter of the atom in the gold foil is not evenly distributed. That most of the atom, as Rutherford expected, is just very low density material that the energetic alpha particles pass through. But somewhere in that low density material would be these tiny, 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 very, very massive particles that were massive enough to be able to reflect back. So that's what we know of the atom, right? That the nucleus is tiny and that the electron forms a huge cloud around the atom of almost massless negative charge. And so most of the particles pass right through, but it's only occasionally that a particle goes close to the nucleus and it deflects, or even more rarely where a particle heads directly to the nucleus and bounces straight back. So that tells us clearly about the very uneven structure of matter. But Rutherford, knowing his physics, know that, for a particle to bounce back, it has to stop. And so we can use what we know about conservation of energy to predict how close did it have to get to the nucleus to that bounce back. And so that's the physics that we do in this. So I'm going to redraw and show you that. Okay, this should allow you to finish. Here's the alpha particle coming out of the radium. It comes out with a kinetic energy. Mass and velocity are given to you. And it's far away, so its electric potential energy at this point is 0. it travels, it slows down, it slows down, it slows down, it reaches the point at which it's going to turn around, and it stops. So the kinetic energy has gone to zero. By conservation of energy, that loss of kinetic energy is now stored in the electric potential energy, kind of like a particle compressing a spring. Or think about a ball going up and reaching its peak where the kinetic energy turns into gravitational potential energy before it comes back down. The same physics. And so the potential energy at this point is K times the charge of the alpha particle times the charge of the gold nucleus times the separation between their centers. And that has to be equal to the kinetic energy that was lost by the alpha particle, which is 1/2 mv squared, because the v here is 0. And so we know everything in this equation except for r. And so Rutherford and you solved for r and discovered that the r was more than 1,000 times smaller than what was expected and known to be the approximate size of the atom, indicating that the nucleus of the atom was less than 1,000 times smaller than the atom itself. And since it's a volume thing, it's 1,000 times 1,000 times 1,000. It makes it makes it hugely smaller than the volume of the atom itself, the volume of the nucleus. So anyway, good luck.